everyone, welcome to another video in the ELEC 2507 lab series. My name's Adam, and today we're going to go through the diode lab. So basically the first little bit of theory shows you the ideal diode characteristics. So the ideal diode characteristic turns on at 0 volts and has a current that goes straight up. But the battery plus resistance model that we're going to use in this class actually has more of a linear slope, where the straight battery model, just a voltage drop across the diode, has a straight current and that turns on at 0.7 volts, and the current actually goes straight up. But realistically, in a real world scenario, we have something that's a little more linear like this. And actually, in truthfulness, the ideal characteristic for a diode is actually an exponential function. So it looks a little different than this, but we'll be figuring that out, and we'll be seeing the differences between the linear model and the exponential model in our simulations. So first, what I'm going to get you guys to do for the pre-lab, for 3.1, make sure you're using the RL value given in resistors.pdf. And that will just have you have a different current through your load. And on top of that, the voltage drop across the load should be proportional to the RS value here. So if you have a really small load, let's say here, and the 20 ohm resistance here, you're actually going to drop quite a bit of your input voltage over your source input here. However, if RL is very large, then you're actually going to drop most of that voltage over the load and the diode. So just remember that. Next, I want you to keep your current for 3.2 below the ID value given in resistors.pdf. So let's go ahead and I'll just open those up. If I go into the lab 3 section, I can go ahead and download the resistors.pdf file along with the lab 3 multisim file. So I'll go ahead and open that in a new tab. And I will download the multisim file, which I already have on my computer. So in this case, if I'm on station number 1, I'd be working with an RL of 100 ohms for 3.1. And for 3.2, I'd be working with an ID that I want to keep under 20 milliamps. So basically, the way to do this is to actually create a loop. So you're going to do loop analysis using the current through this resistor, the voltage drop, and the current across this diode, and as well the current across the load. And next, I want you to keep the current in the load for the bridge rectifier around the same amount. So here we're going to use 10.6 volts RMS. We're going to subtract 2 diode drops from that, right? Because there's always 2 diodes that are on. We're also going to subtract the drop across the diode and the current across the diode and the diode's resistance, as well as the current across the load. And that will make up our loop analysis for this particular circuit here. So the first step it asks us to do is build the circuit in figure 4. So we can go ahead, back up, and actually all the parts, before we start, all the parts that you need for all the experiments are actually given inside the multisim file. We'll go ahead and open it up. So you won't have to add anything to these schematics other than the parts here on the right. So multimeters and oscilloscopes, you'll have to add those. So the multimeter is the very top one on the top right, and the oscilloscope is the 1/4 from the top, and it's a 2-channel oscilloscope. So we can go ahead and drag a couple of those in for now, just so we can copy and paste the elements through our circuits. So what the first section is asking us to do, it's asking us to recreate the figure 4 in the pre-lab, so 3.1 for the pre-lab. We're going to use a 1N4006 diode, which is already given in the schematic. And we're going to use the RL value that was given from resistors.pdf in 3.1 of the pre-lab. And it also says to note from this diagram here how to connect the P and N terminals. So we see the P terminal is the broad side of the actual triangle here. And then we see that the negative side is actually where the triangle comes to a point and then has a parallel line to it, is the actual negative side of the diode. So make sure you're connecting it properly. If you're connecting the positive side of the voltage to the negative terminal, it's never going to turn on. So this is a circuit that we're trying to wire up. All the components are there for you guys, and you can go ahead and just wire that up. So this is what your circuit should look like somewhat. And then from there, I'll go ahead and I'll actually switch my load. So I'm going to use a load of 80 ohms for my particular video, just because that's different than any values that I've given you guys. And I'm also going to put negative 5 volts here for the DC voltage, right? So from there, we can go ahead and run the simulation. Actually, first we'll put a multimeter in so we can actually measure the voltage on the load. We're asked to measure the DC voltage on the load. So go ahead and open up the multimeter, switch to DC, then switch to voltage, and go ahead and hit run. So we can see now across my load, I virtually have 0 voltage drop. That can be considered for all intents and purposes 0. So don't worry about writing the negative 4.24 microvolts. Just call it 0. And we'll look at the voltage drop across the diode as well. And we can see that the voltage across the diode is also 0 at this point. So we'll put that one first. And then we'll keep increasing this step of the DC supply in steps of 1 volt until we end up at positive 5 volts. So from here, we'll go ahead and say we have negative 4 volts across the diode at negative 4 volts at the input, and we still have 0 volts across the load. That makes sense because the positive terminal of the diode is here, the negative terminal is here, right? And we're applying a negative voltage. So if this negative voltage goes to this positive terminal, this diode will never turn on. So keep going, negative 3. And make sure as you're doing this, you're taking these values in an Excel table. So you can go ahead in here and recreate voltage across the load, voltage across the diode, and then IL equals ID. And then one more column that we want you to put, which is the small signal resistance. So RD there, which is just the voltage on the diode divided by the current through the diode. So we can go ahead and switch this now to negative 2 volts. And note those values. Still, the voltage across the load is 0 volts, you can say. Negative 1, 0. And then we'll go to 1 volt, where we'll actually find a change, because that 1 volt will be above the turn-on threshold for the diode, and we're actually applying a positive voltage to the positive terminal here. So go ahead, and we'll see that we have a slight voltage drop across the diode. This is like the minimum turn-on voltage, basically. And we see that we actually have a slight voltage drop across the load, and the rest of the voltage that's not getting dropped across here. So the total of the 1 volt is actually getting dropped across the source here, which is 50 ohms, which is actually quite comparable to the resistance of this node here, right? So we know that we're not going to be dropping much more across this whole branch than we are across here. That'll really become apparent as we increase our voltage here. So let's go ahead to 2 volts. Stop and start. And we see the voltage across the diode slightly increased, but it's not going to increase dramatically. So the maximum forward voltage for this diode is approximately 0.7 or 0.75. So no matter what voltage we apply here, even 100 volts, 1,000 volts, we're only ever going to see about a 0.7 to 0.75 voltage drop across that diode. And that means that the rest of the voltage in the circuit, so the rest of the 2 volts, has to drop across either the load or the source impedance. And because the load and the source impedance are so close in value, we see that we actually lose about half the input voltage here, right? We're inputting 2 volts, and we can see that we're only getting out about let's say 1.4, 1.5 volts between the diode and the load. And that means the rest, another half a volt, is actually dropping here across the source. So let's go ahead and increase that there to 3 volts. And we can see the diode drop doesn't increase very much, but the load drop increases quite significantly. And actually, the voltage drop across the source is actually getting greater and greater, which makes sense as to what I said before. So go ahead and switch that to 4 volts. Again, same sort of thing. We can see that the maximum never actually happens. The maximum forward voltage for this diode never actually happens. And that we actually are only dropping around 2.7 volts of the 4 volts that we're actually inputting into the circuit. So we're losing around 1.3 volts to our source here. And last but not least, we'll try 5 volts. Hit run. And same scenario that we're just talking about. So make sure you're noting all these values as you're going. And you can actually place, if you want to calculate current by doing voltage through the branch divided by the actual resistance of the branch, that's fine. But throughout all these steps, you could have also put a current probe, which will give you the current through the branch, the DC current. Make sure you're looking at the DC point, not I peak to peak, not I RMS, just the DC point. And from there, we can take all the values we need, right? So we see that we have the IDC point, we have the voltage drop across the diode, and we have the voltage drop across the load, which is all the parameters that it's asking us for in this table. From there, we can fill out the table, and then actually insert a plot by going scatter and just adding a plot. So you guys can do that on your own. I'm not going to show you how to do that. I'm sure you're well versed in handling Excel spreadsheets, or whatever tool you guys would like to use for graphical analysis. MATLAB is fine, Mathematica, whatever floats your boat. Alright, so now once this step is done, go ahead and close the multimeters and stop the simulation. And we're asked now to actually hook up the next circuit, which is 4.2, and that is actually the 3.2 from your pre-lab. So you can go ahead and hook it up as shown, and make sure you're using an RL value that you've chosen to keep the current below the specified ID in resistors.pdf. So in my case, I'm going to use 5 milliamps for my maximum ID, and that's just different than any values that you guys got. So I calculated my load resistance to be approximately 630 ohms, and that'll keep my current under 5 milliamps at all times. And the way I did that was just basic loop analysis. So if we go back to the lab manual, it's asking for a 10 volt peak to peak signal. So 5 volt peak at 5 hertz. So if we go back in here, we can add 5 volt peak. At 5 hertz. And then go ahead and add in an oscilloscope. So we already have an oscilloscope block. Instead of actually using this one, why don't we just go ahead, copy and paste it, and we'll just add it in to our diagram there. So it's asking us to look at the voltage across the load again. It's also asking us to change the time scale to 100 milliseconds when we first get in there, and maybe use the single sequence instead of a normal run. So let's go ahead and actually run this simulation once more. We can open it up, change this to 100 milliseconds like it asks us to. 100 or even 200 is good too. And then actually change the scale of the channel. So we can make the waveform slightly bigger. That'll just help us view it. And then go ahead and hit single. And then we should get a nice looking waveform on the screen like that. And go ahead. So basically something is happening with the LED right now. And there's no visual indicator here right now because we're running a straight AC signal. But if there was, what would you expect to see here? So we know that it's taking in a sinusoidal wave, right? And every time that sinusoidal wave gets above the threshold to turn on LED 1, the LED should turn on, right? And then every time the voltage here drops below that threshold, so below the 1.5 volts or whatever it takes to turn on that LED, then we'll know that the LED should be off, right? There should be no light coming from it. So basically, what would that infer about the behavior of the LED happening right now? You could answer that question. And it's also something you guys are going to see during your hardware portion. You're going to have basically the same setup, but instead of the LED being up here, you're going to have a light bulb as a load. And then you're going to see how the AC signal actually affects the turning on and off the light bulb. So when you're taking a screenshot of this, make sure you're putting in your markers where they need to be to show peak-to-peak voltage and to show it's 2.989, which makes sense, right? Because we have approximately a 1.1, 1.2 volt drop from this diode, right? And we have 5 volts peak to peak coming in here, right? So 5 minus 1.1 to 1.2 gives me approximately 2.9. So we're in the right ballpark. And you can go ahead and take a screenshot of that for your report. Make sure it's nice and blown up so you can get a nice, good picture. All right, so next, guys, it's going to ask us to actually increase the DC offset on the LED until we have 1.65 volts of DC voltage on the load, okay? That means we have 5 milliamps running through our circuit. So we're going to increase the offset on the function generator until the DC voltage on RL reaches a value of RL times 5 milliamps. So in everyone's case, it's going to be slightly different. In my case, I'm using a load of 630 ohms multiplied by 5 milliamps, and that will give me approximately 3.15 volts. So that's the number that I'm looking for. That's my magic number on the DC portion of the load to actually give me what I need. So I'm going to go ahead and switch this to a 1 volt peak to peak signal, which is 0.5 volts peak. Go ahead and stop for now. And I want to go ahead and add a voltage probe as well. Voltage probe will just help me see the DC voltage on this particular node here, which is the one I'm interested in. And then scope channels, we're going to actually add channel A to the left side of the LED, and we're going to add channel B now to the right side of the LED. And that just helps us measure on one side of the LED and the other side of the LED, because then we can get a difference between those two, and then we can see the small signal voltage drop across the diode. Make sure you're hooking up the negative channel on the B as well. And everything is set. You can go ahead and hit run once more. And we can see that right now we have 0 volts DC, right? Because I haven't increased the offset at all. So my offset that I'm looking for at this particular node is 3.15 volts. So chances are I'm going to have to be higher than that on my offset to actually achieve that, right? So let's try 4, just for a starting point. And we can either go up or down depending on what we see. Yeah, so we see we're only at 2.1 volts DC on that node. So let's increase that a little more. 5 volts maybe, 5.5 maybe even. So that's a little high now. So I'll go back down. So 3.19, that's right in the ballpark, but we can make it better since we're working in simulation. So go down to 5.15 maybe. And we can see now we're perfect at 3.15. If we added a current probe just to check as well, we should see that the current through the load is exactly 5 milliamps, right? Which is what we calculated. So that makes sense. Now we can see the visual indicator is actually happening for the LED now, right? And what's happening is the LED is blinking currently. And why is that? It's because the LED is just in a turn-on state. Okay, so the DC voltage is just enough to supply to the load and the LED so that the LED will constantly be on the threshold of turning on. But the 0.5 volts peak signal, it goes down 0.5 volts and it goes up 0.5 volts, right? So in the cycle where it goes down 0.5 volts, what's going to happen is the LED is going to turn off, right? Because the operating point is centered around the DC operating point, and it's going down 0.5 volts, it's going up 0.5 volts like we talked about in the last lab. So basically, the LED is going to turn on and off every half cycle. So these last two steps, it wants us to do some calculations. But actually, there's easier way to find that stuff now that we're using software. So go ahead and go back into the simulation. And we've already placed this current probe, right? And what are we looking for? We're actually looking for the peak-to-peak current. And in this case, that value is actually our ID value. Okay, so small ID is actually I peak to peak right here. So in my case, it's 1.45 milliamps. And then last but not least, we're looking to divide the small signal voltage on the diode by the current through that diode, right? And that will give us the resistance of the diode in AC terms. So now let's open up our scope channels. And this is where it gets a little bit tricky. So bear with me. Hit auto. Get two waveforms on the screen. Once you have the two waveforms on the screen, it might look a little bit like this if you hit single and just hit your edges and try to get a waveform on the screen. But that's fine because we're only worried and taking one measurement, and we can take it somewhere over here, let's say. What we're going to do is get a single waveform, and we're going to take one marker and put it at the peak, the other at the minimum, and that should line up with the peaks and minimums of the bottom wave as well. And then you can actually get the difference between channel A and channel B, okay? And that will be the drop across the diode. So in my case, I have 925.35 minus 910.24. And I can see that difference is around 15.103 millivolts between the two channels. So now, if I take a screenshot of that wave and include it in my report, I'm good for this section, and I have the small ID and the small VD that I need to do the final calculations for this step. So go ahead back to the lab manual. Now that we have VD, which is 15.103 millivolts, I said, from my experiment, and we also have the 1.45 milliamps that was given from the previous step, where we actually looked at the current here, right? The 1.45 milliamps peak to peak. And so if we go back here and we do the division of those two, we can find that our small signal resistance, RD, small RD, in my particular case, is 10.41 ohms. And that makes sense. So everyone's values are going to be slightly different, and everyone's values will vary from around 10 to 20 ohms, I'll say here. If you're outside of those margins slightly, that's okay. I didn't calculate everyone's by hand, but yeah, make sure you're somewhere in that range. So next, this may be the coolest circuit you guys get to make in all of your undergrad. I have a lot of fun making these circuits, and there's so many applications for making at-home power supplies to power delivery to PCBs to anything you would want to use power for, basically. So what a bridge rectifier aims to do is transfer an AC signal, so a wall signal, into something that can be easily managed by, let's say, something like your television, your smartphone. So anytime you grab a wall wart and you plug it into the wall and plug in your iPhone, this is the basic principle of what's happening. It's bridge full wave rectification, and it goes into a couple capacitors which actually chop the signal, and then you end up with a DC wave. So let's go ahead and construct it. So basically, what we're going to need is 10.6 volts RMS on the input. And the way we're going to do that is actually using a transformer, as you see here. So the transformer right now has a 10-to-1 turns ratio. But let's say we're coming out of wall power, right? And wall power has 120 volts RMS. So basically what we're looking to do is transfer 120 volts RMS into 10 volts RMS. And if you guys remember your transformer equations, the way to do that is just to do 120 divided by 10.6 to find a ratio of turns that are needed between the primary and the secondary to actually give that voltage. And when I did that calculation to do 120 divided by 10.6, I found my turns ratio for this particular transformer should be around 11.32 volts. With that said, I hook it up like that, and I can place a multimeter just to verify that the RMS voltage that I'm seeing there is what I want it to be, right? So let's go ahead and hook that up like so, and I'll go ahead and switch that to volts. Yeah, and I can see that I have exactly 10.6 volts, which I expected, right? Because I was inputting 120 volts RMS. I stepped down at 11.32 to 1 turns ratio, and that's what I calculated. So from there, we can go ahead and place all the other components in our circuit. So I'm going to go ahead and move these capacitors for now. Those are more just to show you later on how this circuit is exactly like what you're doing in a hardware setting. But either way, all you'll have to do really for this circuit is just hook up that output node like so. We'll also want to keep the current through the LED and through this branch below a certain value, right, which was specified in resistors.pdf, and it's the same value you use for ID in 4.2. So my value for ID again is 5 milliamps, and I've calculated that then I should keep my resistance here under approximately 1540, so 15.40k, or sorry, 1.54k. So it's asking us to actually connect the load across both terminals of the oscilloscope. And sometimes these wires aren't long enough. You see there's only black there, and that sometimes makes it hard to connect wires, so just drag it down a little bit, then you'll be able to connect that second scope channel, just like so. Go ahead and hit run, and now we see we have 10 volts RMS being transferred into a sort of DC wave, and we can go in here and check it out, see what it looks like. You can see that it sort of looks like a DC wave, right? So it's rectifying the bottom half cycle. There is no bottom half cycle wave anymore. And we actually have an average DC output. So if we go ahead and place a voltage probe somewhere right there, so we can see that we have a DC output that is due to this waveform here. If you also notice that the frequency is doubled here, right? And why is that? It's because we rectified the bottom wave. So now that every time the wave goes up and down, it's just restarting a new cycle. So this could work as a rudimentary frequency doubler. I know it wouldn't be a very good one, but this is something you guys will learn in later classes, and it's a cool application. For this is how you could make a frequency doubler. So as we see here, the bottom of the wave is actually at around 1.253 volts, and that makes sense because the wave won't even turn on the LED until we get to around 1.4, 1.5 volts, and then it will start conducting and dropping voltage across the load. So make sure you put those markers in, have a screenshot of your peak-to-peak values, and yeah, should be good. As well as a screenshot of the average, or at least just note down the average DC output so you can write that down in your report. And last, just to check, we can see that the current through this node is actually always kept below 5 milliamps, and that is satisfying our condition from resistors.pdf, which was asking for ID to be kept below a certain value. So just make sure you're doing that every time so you know you picked the right resistance value. So from there, guys, I would like you to actually add in these two capacitors. And the reason for that is just to basically see the functionality of what you're going to be making in the hardware setting. So you actually don't have to take any values here. This is all for your own personal learning. But go ahead and hit stop. Make sure these two capacitors are connected. And now they're both connected. Okay, so now when we hit run, we should see a chopped signal, right? One that can constantly turn this LED on because it's now been transformed from a sinusoidal to a DC signal. So we can see that now we'll put the voltage probe back on the output node. And we can see now that there's basically no peak-to-peak voltage on that output node. It's basically, for all intents and purposes, that is not changing at all. And the DC and the RMS are almost identical, and that makes sense. If we go look at the actual waveform that we're seeing here, and maybe switch to a different time scale where we could see multiple sections of waveform, we'll also increase the scale too. To 5 volts per division. And we can see we're offset by 13.3 volts, right? So, knowing that the scale is 5 volts per division, what will we have to go down by in divisions here to offset by 13.3? And that should be around just over 2. 2.6. So if we go ahead and divide 13.3 by 5, we should see that we know we need 2.66 divisions for this waveform to be centered in the very middle, and we're at 2.6 and we're almost centered, so that makes sense. We can see that this is a purely DC wave at this point. If we put our markers on there, there's basically no difference between marker A and marker B well, there is a slight difference, I guess, but it's so small to the second decimal that we can actually just neglect it and say this is just a DC wave for all intents and purposes. Any load that's going to be seeing that wave is going to treat it as a DC wave, and that makes intuitive sense to what we're seeing here on the LED, right? We see there's no more flashing on the LED. We see the red sign on the LED is completely solid, and that means the LED is constantly on because it constantly has enough voltage to bias this PN junction and forward bias it. All right, enough of that. We'll get on to the last circuits in figure 7. So basically what we're going to do here is we're going to observe and sketch the output waveforms. So the way we're going to do that is we're just going to put in an oscilloscope, and the output waveforms are going to be between there and sometimes, again, we'll have to make this node a little bigger. Now we see there's a red part between the two. Sometimes it'll let us connect it, sometimes it won't. We might have to make it even a little bigger. Make it a little bigger. And we'll drag that down there. All right. So actually, for this step, I've had to split the 10.6 volts RMS up into two different sources because we weren't actually getting convergence on the circuit when we were doing it the other way around. So I'll go ahead and run that simulation. And we can open up this waveform here. And we can see that if we run a single sweep, and we go over to the waveform, we can see that this is actually just below the turn on threshold, right? So this is the forward voltage drop on the one end 4006. And that makes sense, right? Because it's connected in a reverse manner. So we're actually rectifying the negative half cycle, right? Now this is actually the negative half cycle where it goes up to the positive. And the positive half cycle is where it stops conducting. But it will only stop conducting once it gets to a threshold of 643 millivolts. It won't stop conducting before that. So that's why we have this slight dip under the zero axis. So go ahead and place in your markers once more. Place one right at the peak of one wave and one right maybe in the middle here, showing that you have that voltage drop there, and that the entire RMS signal is actually being transferred in here, minus one voltage drop of a diode. Okay. So make sure you're showing your scales and taking that screenshot. One last thing, we'll go in and add in one more scope for the last two circuits now. So this circuit is connected between there and here. And the B circuit is connected between there and there. All right, so we can go ahead and remove these connections for now, because now we need to bring our input nodes to our other circuits. So our input's between D3 and D4, and the scope is looking between those same channels on channel A. So if we go ahead and run the simulation, and we'll decrease the scale just to make our waveform a little bigger for us, and we'll go ahead and bring in the cursors again. We can see we go up 600 millivolts and down 600 millivolts. So we're getting quite similar to what we had in the previous scenario on the bottom of the waveform, right? But now we're getting that same thing happening in the positive and the negative half cycle. So we're going up 645, we're going down 645, and that's about it. So last but not least, we can take a screenshot of that one with the markers labeled at the peak values for each individual diode. And then, last but not least, we can run the last simulation. So go ahead and remove those wires once more. And we will now go and place them on the input of that node and the input of that node as well. So now we're going to need channel B on the scope. So go ahead and hit run. It's a single sweep, so we might have to change the trigger to channel B instead. And then go ahead and increase the scale again and put the markers where they should be. If the markers aren't on the right channel, just go ahead and right click, go select trace, and go channel B. And now they'll be placed on the right channel. And now we can see that we actually have double what we had before, right? So that makes sense because there's 2 diodes at each half cycle, right? So instead of just the regular 645, we have 2 times 645, which gives us around 1.289. And we can go ahead and take a screenshot with those markers in place, just like so, and comment on the results, just like I was sort of commenting all throughout. Why is this happening? What are the diodes doing in each half cycle that are making this RMS signal clip? And yeah, that's about it. Other than that, I will get back to you guys with the hardware portion of this lab, and good luck. Bye-bye.